Okay, we are going to now start our next unit. We're going to do one section from chapter 5, which we will do today, and then we will jump into chapter 6, as I recall, or is it 7? Well, that's okay. It's either 6 or 7. All right, so that's where we're headed. So one section of chapter 5, because I want to continue using combinations, and you folks all know how to do combinations. So I think it'd be interesting to do this section of combination and probability problems. But before we do that, very fascinating video on ways to spot a bad statistic as done by Mona Calabi. Just to give you a hint, you should try to determine what those 3 ways are as she's going through this very, very short lecture, and take note of those 3 ways to spot a bad statistic would make an excellent, excellent test question.
Now, I'm going to be talking about statistics today. If that makes you immediately feel a little bit wary, that's okay. That doesn't make you some kind of crazy conspiracy theorist. It makes you skeptical. And when it comes to numbers, especially now, you should be skeptical. But you should also be able to tell which numbers are reliable and which ones aren't. So today I want to try to give you some tools to be able to do that. But before I do, I just want to clarify which numbers I'm talking about here. I'm not talking about claims like 9 out of 10 women would recommend this anti-aging cream. I think a lot of us have always rolled our eyes at numbers like that. What's different now is that people are questioning statistics like the US unemployment rate is 5%. What makes this claim different is that it doesn't come from a private company, it comes from the government. And actually now, about 4 out of 10 Americans distrust the economic data that gets reported by government. Among supporters of President Trump, it's even higher, it's about 7 out of 10. Now, I don't need to tell anyone here that there are a lot of dividing lines in our society right now. And a lot of them start to make sense once you understand people's relationships with these government numbers. See, on the one hand, there are those who say that these statistics are crucial, that we need them to make sense of society as a whole in order to move beyond emotional anecdotes and measure progress in this objective way. And then there are the others who say that these statistics are elitist, maybe even rigged. They don't make sense and they don't really reflect what's happening in people's everyday lives. Now, it kind of feels like that second group is winning the argument right now. We're living in a world of alternative facts where people don't find statistics this kind of common ground, this starting point for debate. This is a problem. There are actually moves in the US right now to get rid of some government statistics altogether. Right now, there's a bill in Congress about measuring racial inequality. The draft law says that government money should not be used to collect data on racial segregation. This is a total disaster. If we don't have this data, how can we observe discrimination, let alone fix it? In other words, how can a government create fair policies if they can't measure current levels of unfairness? And this isn't just about discrimination, it's everything. Think about how can we legislate on healthcare if we don't have good data on health or poverty? How can we have a public debate about immigration if we can't all at least agree on how many people are entering and leaving the country? Statistics come from the state, that's why they got their name. And the point was to better measure the population in order to better serve it. So we need these government numbers, but we also have to move beyond either blindly accepting or blindly rejecting them. We need to learn the skills to be able to spot bad statistics. Now, I started to learn some of these when I was working in a statistical department as part of the United Nations. And our job was to find out how many Iraqis had been forced from their homes as a result of the war and what they needed. It was really important work, but it was also incredibly difficult. Every single day, we were making decisions that affected the accuracy of our numbers. Decisions like which parts of the country we should go to, who we should speak to, which questions we should ask. And I started to feel really disillusioned with our work because we thought we were doing a really good job. But the one group of people who could really tell us were the Iraqis, and they rarely got a chance to find our analysis, let alone question it. So I started to feel really determined that the one way to make numbers more accurate is to have as many people as possible be able to question them. So I became a data journalist, and my job is finding these data sets and kind of sharing them with the public. And anyone can do this. You don't have to be a geek or a nerd. You can ignore those words. They're used by people who are trying to say they're smart while pretending they're humble. Absolutely anyone can do this. So I want to give you guys 3 questions that will help you be able to spot some bad statistics. So question number 1 is, can you see uncertainty? Now, one of the things that's really changed people's relationship with numbers, and in fact, even their trust in the media, has been the use of political polls. Now, I personally have a lot of issues with political polls because I think that the role of journalists is actually to report the facts and not attempt to predict them, especially when those predictions can actually damage democracy by signalling to people, don't bother to vote for that guy, he doesn't have a chance. Anyway, let's set that aside for now and talk about the accuracy of this endeavour. So, based on national elections in the UK, Italy, Israel, and of course the most recent US presidential election, using polls to predict electoral outcomes is about as accurate as using the moon to predict hospital admissions. Now, seriously, I used actual data from an academic study to draw this. There are a lot of reasons why polling has become so inaccurate. Our societies have become really diverse, which makes it very difficult for pollsters to get a really nice representative sample of the population for their polls. People are really reluctant to answer their phones to pollsters, and also, shockingly enough, people might lie. But you wouldn't necessarily know that to look at the media. For one thing, the probability of a Hillary Clinton win was communicated with decimal places. We don't use decimal places to describe the temperature. How on earth can predicting the behaviour of 230 million voters in this country be that precise? And then there were those sleek charts. See, a lot of data visualizations will overstate certainty, and it works. These charts can numb our brains to criticism. When you hear a statistic, you might feel skeptical. As soon as it's buried in a chart, it feels like some kind of objective science, and it's not. So I was trying to find ways to better communicate this to people, to show people the uncertainty in our numbers. And what I did was I started taking real data sets and turning them into hand-drawn visualizations so that people can see how imprecise the data is. So people can see that a human did this, that a human found the data and visualized it. So, for example, instead of finding out the probability of getting the flu in any given month, you can see the rough distribution of flu season. This is a bad chart to show in February, but it's also more responsible data visualization, because if you were to show the exact probabilities, maybe that would encourage people to get their flu jabs at the wrong time. Now, the point of these shaky lines is so that people remember these imprecisions, but also that they don't necessarily walk away with a specific number, but they can remember important facts. Facts like injustice and inequality leave a huge mark on our lives. Facts like Black Americans and Native Americans have shorter life expectancies than those of other races, and that isn't changing anytime soon. Facts like prisoners in the US can be kept in solitary confinement cells that are smaller than the size of an average parking space. Now, the point of these visualizations is also to remind people of some really important statistical concepts like averages. So let's say you hear a claim like the average swimming pool in the US contains 6.23 fecal accidents. Now, that doesn't mean that every single swimming pool in the country contains exactly 6.23 turds. So in order to show that, I went back to the original data, which comes from the CDC, who surveyed 47 swimming facilities, and I just spent one evening redistributing poop, so you can kind of see how misleading averages can be. Okay, so the second question that you guys should be asking yourselves to spot bad numbers is, can I see myself in the data? Now, this question is also about averages in a way, because part of the reason why people are so frustrated with these national statistics is they don't really tell the story of who's winning and who's losing from national policy. It's easy to understand why people are frustrated with these global averages when they don't match up with their personal experiences. So I really wanted to show people the way that data relates to their everyday lives. So I started this advice column called Dear Mona, where people would write to me with questions and concerns, and I would try to answer them with data. People really ask me anything, questions like, is it normal to sleep in a separate bed to my wife? Do people regret their tattoos? What does it mean to die of natural causes? And all of these questions are great because they really make you think about ways to find and communicate these numbers. If someone asks you how much P is a lot of P, which is a question that I got asked, you really want to make sure that the visualization makes sense to as many people as possible. Now, these numbers aren't unavailable. Sometimes they're just buried in the appendix of an academic study. And they're certainly not inscrutable. If you really wanted to test these numbers on urination volume, you could grab a bottle and try it out for yourself. The point of this isn't necessarily that every single data set has to relate specifically to you. I'm interested in how many women were issued fines in France for wearing the face veil or the niqab, even if I don't live in France or wear the face veil. See, the point of asking where you fit in is to get as much context as possible. It's about zooming out from one data point, like the unemployment rate is 5%, and seeing how it changes over time, or seeing how it changes by educational status. This is why your parents always wanted you to go to college. Or seeing how it varies by gender. Nowadays, male unemployment rate is higher than the female unemployment rate. Up until the early 80s, it was the other way around.
Oh yes, don't you just love pop-ups? So let's see here. If I can continue on.
See, this is the story of one of the biggest changes that's happened in American society. It's all there in that chart once you look beyond the averages. The axes are everything. Once you change the scale, you can change the story. Okay, so the third and final question that I want you guys to think about when you're looking at statistics is, how was the data collected? So far, I've only talked about the way that data is communicated, but the way it's collected matters just as much. And I know this is tough because methodologies can be opaque and actually kind of boring, but there are still some simple steps you can take to check this. So I'll use one last example here. One poll found that 41% of Muslims in this country support jihad, which is obviously pretty scary, and it was reported everywhere in 2015. Now, when I want to check a number like that, I'll start off by finding the original questionnaire. And it turns out that journalists who reported on that statistic ignored a question lower down on the survey that asked respondents how they defined jihad. And most of them defined it as, quote, Muslims' personal, peaceful struggle to be more religious. Only 16% defined it as violent holy war against unbelievers. Now, this is the really important point. Based on those numbers, it's totally possible that no one in the survey who defined it as violent holy war also said they support it. Those two groups might not overlap at all. It's also worth asking how the survey was carried out. This was something called an opt-in poll, which means that anyone could have found it on the internet and completed it. There's no way of knowing if those people really even identify as Muslim. And finally, there were 600 respondents in that poll. There are roughly 3 million Muslims in this country, according to Pew Research Centre. That means the poll spoke to roughly 1 in every 5,000 Muslims in this country. Now, this is one of the reasons why government statistics are often better than private statistics. A poll might speak to a couple hundred people, maybe 1,000, or if you're L'Oreal trying to sell your skincare products in 2005, then you spoke to 48 women to claim that they work. See, private companies don't have a huge interest in getting the numbers right. They just need the right numbers. Government statisticians aren't like that. In theory, at least, they're totally impartial, not least because most of them do their jobs regardless of who's in power. They're civil servants. And to do their jobs properly, they don't just speak to a couple hundred people. Those unemployment numbers I keep on referencing come from the Bureau of Labour Statistics. And to make their estimates, they speak to over 140,000 businesses in this country. Now, I get it, it's frustrating. If you want to test a statistic that comes from a private company, you can just buy the face cream for you and a bunch of friends, test it out, and if it doesn't work, you can say the numbers were wrong. But how do you question government statistics? Well, you just keep on checking everything. Find out how they collected the numbers. Find out if you're seeing everything on the chart that you need to see. But don't give up on the numbers altogether, because if you do, we'll be making public policy decisions in the dark, using nothing but private interests to guide us. Thank you.
Great TED Talk on statistics and 3 ways to spot a bad statistic. All right, so let's jump into chapter 5, section 3, and talk a little bit about how we can use combinations in probability problems. Now, I want to go back to a problem we talked about, oh my word, when we first started chapter 4. If you toss 3 coins, what's the probability of getting 2 heads and a tail? And I told you back in chapter 4 that some people say, well, when you toss 3 coins, you have 4 probabilities. You can get 3 heads. You could get 2 heads and a tail, 2 tails and a head, or 3 tails. There's 4 possibilities. So that means, what's the probability of getting 2 heads and a tail? 1 out of 4. But that's wrong, because there's only one way of getting 3 heads. They're all heads. There are 3 ways of getting 2 heads and a tail. You could have the first 2 heads and a tail, the outer one's heads and the inner one a tail, the first one tail, and the last, there's 3 different ways of getting 2 heads and a tail, 3 different ways of getting 2 tails and a head. So you got to make sure, here is the sample space, by the way. You've got to make sure you have the entire sample space. And that's what we're going to be talking about today on these probability problems, and finding a shorter way then eventually of doing the problems. Okay, there is roughly an 80% chance that a 20-year-old person will be alive at age 65. Suppose 3 people at age 20 are randomly selected. Find a probability exactly 2 will be alive, most 1, at least 1 will be alive at age 65. Okay, first we're going to find all the probabilities because we want to get the entire sample space, just like in the coin problem. All right, so we could have all 3 alive at 65. We could have 1 dead at 65, but which one could it be? It could be any of those 3. So there's 3 possibilities, you see? You could have 2 dead at 65, but which 2? Right? Or you could have all 3 dead at 65, okay? Now, let's talk about the probability of each possibility. If everybody's going to be alive, 80% chance that a 20-year-old person will be alive. This person being alive has nothing to do with the second person being alive. They're independent events. And remember from chapter 4, independent events mean you can multiply. So this would be 0.8 times 0.8 times 0.8, or 0.8 cubed. Yeah? Okay? Each one of these, what's the probability of 2 alive? That's 0.8 times 0.8 times the dead is 0.2, because if it's 80% chance they're alive, it's 20% the chance that they're dead. So this is 0.8 squared times 0.2. Same thing here. Same thing here. Yeah? Now, what about having 2 dead out of the 3? 2 dead, the probability of getting 1 dead is 0.2. So this would be 0.2 squared times 0.8. And each of these likewise. And finally, all 3 dead would be 0.2 cubed. So I found the probability of each possibility. All right, now let's find a probability of distribution where X is the number alive at 65. So what we want to do is we want the number alive and the probability. So I have 0 alive, 1, 2, or 3, and now we got to find a probability. Probability of 0 alive, okay, would be that they are all dead. So I've got to do 0.2 cubed, and 0.2 cubed should be 0.008, I think. Try that again, 0.2 cubed. Heaven's sakes, it's a rough day. Try this again, 0.2 raised to the 3rd, darn it. Yeah, it's 0.008. Okay, how about 1 alive? 1 alive happens right here. So I have 0.2 squared times 0.8. And then I got to take that times 3 because there's 3 of those. And I get 0.096. What about 2 alive? 2 alive is right here. So I've got to take 0.8 squared times 0.2 and then times 3 of those because there's 3 there. 0.384. And then finally, what about all 3 alive? 0.8 cubed. And I get 0.512. One good check to see if you've done this correctly is add these up. And they should add up to 1 whole or 100%, right? So 20, bingo. Okay, 1 or 100%. All right. So I first found all the possibilities. I found the probability, and then I found the probability distribution. Okay. Now we still have not answered the questions up here. So let's go to the next screen. So here I have the totals as I just wrote them down there. The probability at most 1. If you have at most 1 person being alive, that means you either have 0 alive or 1. So you have to add up 0 alive or 1. Add those 2 up, 0.104, or about 10%. That at most 1. How about the probability of at least 1? Could be 1, could be 2, could be 3. You can add these 3 up here, or you could take 100% minus the probability of 0, right? And you're going to get 0.992. So it's like 99% chance there's going to be at least one person alive, all right, at age 65, okay? Now, this is a kind of a heck of a lot of work, listing all the possibilities and then finding all the probabilities. So in other words, wouldn't it be great to have a shorter way of doing it, okay? And that's what we're going to talk about next, a shorter way of doing it. All right, on page 237, problem 5.47 is talking about an ailment that children can get, which is called having a pinworm, okay? Doesn't sound like something very pleasant, but there is a treatment for pinworm, and it's 90% effective, okay? So we want to find a probability that exactly 2 of the 3 children are cured. All right, we're going to do the whole chart just to go through once again and repeat how this is done. So if you have 3 kids, you could have them all cured. You could have 2 cured and 1 not, right? And we don't know which one is not cured, so it could be the last, the second, or the first kid. You could have 2 not cured, okay? And 1 cured. We don't know which one, so once again, we have to list all the possibilities. And we could potentially have no one cured, okay? All right, we know the cure is 90% effective and it's 10%, it's not gonna help. So what's the probability? These are all 3 children that are independent from each other. We can multiply. This would be 0.9 times 0.9 times 0.9, which is 0.9 cubed. This would be, right? This would be 0.9 squared times 0.1, correct? Each one of these would be that, all right? This one down here could be 0.1 squared because 2 of them are not cured and 1 is, okay? And down here would be 0.1 cubed if no one is, all right? So now, 0.9 cubed is 0.729. Okay, each one of these is going to be 0.9 squared times 0.1, which is 0.081. Each one of those is 0.081, and 3 of them times 3 is 0.243, okay? 0.1 squared times 0.9 is 0.009, but there's 3 of those, 0.027. And finally, 0.1 cubed is 0.001, I think. Should know that off the top of my head. Sure, it's 0.001. All right, so there, we've listed the whole chart, okay? We want to find a probability that exactly 2 of the children are cured, 2 of them are cured here, so the answer should be 0.243, okay? Now, instead of doing all this work, can't we jump to this right away? And there's a nice, easy, shortcut way of jumping to this. First, if you're going to have 2 out of 3 kids, 2 out of 3 kids is how many ways can I pick 2 out of 3 kids? Combinations, right? Combinations. So that's how many ways we can pick 2 out of 3 kids. Now, what's the probability? The probability of a cure is 0.9, and 2 of them are cured, squared, times 0.1 that's not, right? And that is precisely the same answer as 0.243. Okay, you can do it. Find a 3C2, okay, and take that times 0.9 squared times 0.1. And I get 0.243, or about 24.3%. Much, much, much shorter than doing the chart, okay? All right, this one's a little tougher. It'll be the last one that we do the hard way, okay? But I think it's fascinating to show you a tough one. This is people that have a psychiatric disorder. 20% of the population has a psychiatric disorder, okay? We want to find a probability that exactly 3 out of 4 people have a psychiatric disorder, all right? So let's make the complete chart, go through it, and then do it the short way. All right, so first, you could have everybody has a psychiatric disorder. So I'm going to use D for disorder. So everybody could have the disorder, right? You could have one person with the disorder. I don't know which one, right? So it could be any one of the 4 not have it, and 3 do have the psychiatric disorder. I could have 2 people that don't have. This is 3 people had the psychiatric disorder. I could now do, how about 2 people have it and 2 people don't? So this is going to be D like this, or I could do D, D, or I could do N, D, or I could do, what am I missing? I could do D, N, right? I could do N, D, 1, 2, 3, 4, 5. I'm missing one. D, N, D. Okay, I need N, D, N. Okay, so there are 6 of those. And then what about having 3 that don't have it and 1 that does? 3 that don't, N, D, and we don't know which one. Okay, and finally, all 4 do not have it. Okay, all right, an immense amount of work when you get up to 4 people. All right, so the probability that all 4 have the disorder would be 0.2 for each one. Independent events is 0.2 to the 4th, which is 0.0016, I think. Okay, now what about all 4 of these? These are 3 that don't have it. Pardon me, 3 that do have it. 0.2 cubed times 0.8 for the person that does, 80% chance they don't have it. And 0.2 cubed times 0.8 is 0.0064. And there are 4 of those, so I need to take that times 4, which is 0.0256. Okay? Now I've got 6 of these right here. Okay? 6 of these having the disorder, D and D, would be 0.2 squared times 0.8 squared, because 2 have it and 2 don't. And I get 0.0256 for each one, and there's 6 of those. So it's 0.0256 times 6, which is 0.1536. Yeah? All right, down here, I have 3 that don't. So that would be 0.8 cubed. So 0.8 cubed, and then times the 0.2 for the person that does have it is 0.1024. And we got to take that times 4 of them, which is 0.4096. And finally, we have 4 that don't have it. That's 0.8 for each one. So 0.8 raised to the 4th is, again, 0.4096. Isn't that weird? Okay? You can check yourself, add these all up, and see if it adds up to 1. I think it will. 1536 plus 0.0256 plus 0.0016 equals bingo, 1. Works perfectly. All right, find the probability that exactly 3 out of the 4 have the disorder. 3 out of the 4 have the disorder is 0.0256. Easier way to do the problem. Easier way, how many ways can I pick 3 out of 4? That's 4C3. 3 of them have it. 3 of them have it. So it's got to be a 0.2 cubed times the 0.8. Okay? And you'll get precisely the same thing. All right? Okay, so enough of this work. So let's do it now just with combinations, okay? You go through 10 traffic signal lights. What's the probability you face exactly 4 lights? Now, let's talk a little bit about here. The probability of getting a red light, we're going to call 1 out of 3 because there's 3 lights, red, yellow, and green. We're going to assume, to make things a little simpler here, that the timing, we know that yellow lights are shorter than the red and the green, but we're going to make them all the same amount of time just to make the problem a little simpler. So the probability of getting a red is 1/3. The probability of not getting a red, either a green or a yellow, would be 2/3, okay? All right, we're going to assume they're independent. In other words, whatever light you get on the first light has nothing to do with the second light, okay? All right, so we want to calculate the probability of getting exactly 4 red lights out of the 10. Would that not be a 10C4? Yeah? Okay, that's how many different ways you can get 4 red lights out of 10. Now, because you're going to get 4 red lights, we know that it would be then 1/3 is the chance of getting a red light to the 4th power. It would be 2/3 to get a yellow or a green. That would be raised on the other 6 lights. That would be to the 6th power. Are you with me? Okay? Work that out, and you have your answer. 66% of Americans are convinced that the food they buy is safe. 6 customers are randomly sampled. Find a probability that exactly 4 think their food is safe and 2 doesn't. So if we're sampling 6 people, how many ways can I pick the 4 people out of the 6? So 6C4. You see the beauty of combinations and permutations? You can do all this fun stuff, right? 6C4, and 4 of them think their food is safe. Here's the probability that people think that their food is safe, so it should be 0.66 to the 4th. So you're going to have 4 people that think it's safe. Then you're going to have 2 that don't think it's safe. All right, so the 2 that don't, the probability is that not 0.34, they have to add up to 100%, right? Just like the 1/3 and 2/3 here with the traffic lights. This has to add up to 100%. So here are the 2 people that don't think their food is safe, independent events. Square that, and you get your answer. Doing these problems by combinations is so much easier than using a chart. I've got homework problems, a couple problems from the book right off the bat. And then do you see, I've got a bunch of different problems that we did from chapters 3 and 4. Okay, these are extra problems. Make sure you do the extra problems. They count on your homework. Okay, also, as we get further and further into this course, we're now in chapter 5, I'll be doing this. I'll be tossing problems at you occasionally so that you can see what's going on, so you can understand what you did in the past, and so you can have better luck on the final.